So we derived these three different rules for doing numerical integration. We derived the midpoint rule in the last chapter, and the trapezoidal rule and Simpson's rule in just this last video for this section. And just I want to add these here in front of you so you can remember what they are. Remember, really what the differences here are is the midpoint rule, we use the midpoints of all of our subintervals instead of using endpoints. With the trapezoidal and Simpson's rule, we use the endpoints. The delta x's are the same in each case, but Simpson's rule has the additional caveat of we need to have an even in order to make this work. But the important things are these patterns. With the midpoint rule, there's all the values of the functions are multiplied by 1. With the trapezoidal rule, all of them are multiplied by 2 except for the two endpoints. But Simpson's rule has this more complicated pattern where we alternate between 4 and 2. Remember, it goes 1, 4, 2, 4, 2, 4, 2. So the 4 comes before the 2. And then because we're using an even in, it will always end with 2, 4, 1. Let's go ahead and do a problem involving this before we do anything else with it. Just to see it in action again, since we've only done one example of the trapezoidal rule and the Simpson's rule so far. We're going to work on problem 17, where we want to approximate the integral from 0 to 4 of 1 over the cube root of x squared plus 1. And they want to have n equals 8. So again, we have the interval from 0 to 4. We split it into 8 subintervals, where the width of those rectangles, or not rectangles, the length of the subintervals is 4 minus 0 over 8, or 1/2. That means we have our endpoints. Okay, we'll stop there. Go 0, 1/2, 1, 3/2, 2, 5/2, 3, 7/2, and 4. Those are the endpoints that we're going to use in both the trapezoidal rule and Simpson's rule. Actually, I'm not even going to write out the interval again. The integral again. Just going to write the trapezoidal rule is going to say is approximately 1/2 times our delta x. So we have a 1/2 times a 1/2. Now we take the value of the function at 0. So we plug 0 into here. That gives us a 1. So we just get 1 over the cube root of 1. We plug in 1/2. Well, I'm going to simplify it to an easier expression. The f of 1/2 is actually the cube root of 4 over 5. But remember, in the trapezoidal rule, we need to multiply that by 2. So we get 2 times the cube root of 4/5. Now we plug in 1. This one's a little easier. We just have 1 plus 1 in there. We get 1 over the cube root of 2. But of course, in the trapezoidal rule, we also need to multiply that by 2. So we get 2 over the cube root of 2. Now we plug in 3/2. When we plug in 3/2 and simplify, we get the cube root of 4 over 13. But again, this needs to be multiplied by 2. So we get 2 times the cube root of 4 over 13. Plug in 2. Now we get a 5 in here. Again, the integers are a lot easier than halves. But we need to multiply this by 2, so we have 2 over the cube root of 5. Next one, again, we still have a 2, and putting in 5/2, we get the cube root of 4 over 29. Plugging in 3, now we get a 10 in there, but we still have the 2, so 2 over the cube root of 10. Then 7/2, we get 2 times the cube root, this time of 4 over 53. And then finally, When we plug in 4, we get a cube root of 17 on the bottom, and we don't multiply it by 2 this time. So we just have 1 over the cube root of 17. Of course, that's kind of a it looks like kind of a mess, doesn't it? But we're just going to plug into a calculator. And I already did that for us. We get approximately 2.53991. But you can already tell that putting in big N's for some more complicated functions can get a little bit messy. But it is something that a computer can do incredibly easily. So really these numerical integration techniques are for, well, they were developed before computers, but they become very important because of computers. But they would be important because we don't know how to, we can't do this integral in any way. We cannot find an antiderivative for this integral anyways. I don't even know what I would do to even try, and I'm thinking this is one that we cannot find an antiderivative for, even if we did everything possible. So if we needed this particular value, this might be the only way that we have available to us. Okay, Simpson's rule. Now it's going to be pretty much the same thing. In fact, we're going to use the same y values, all the same values of the function. Instead of the 1/2 here, we're going to have a 1/3. The other 1/2 came from our delta x, remember? We're going to use all the same y values, except we're going to go 1, 4, 2, 4, 2, and so on. So every other 2 is going to be a 4 instead. So we're going to have 1 plus 4 cube root of 4 over 5, plus 2 over cube root of 2, plus 4 cube root of 4 over 13, plus 2 over the cube root of 5, plus 4 cube root of 4 over 29, plus 2 cube root of 10, plus 4 cube root of 4 over 53, and then this one doesn't change either. We have 1 over the cube root of 17. So once we've done one of these, the other one is really simple. You just change a few numbers. Of course, that means you get to plug it all into a calculator all over again. It's really fun to do, I admit. Sarcastically, at least. Okay, so Simpson's rule gave me approximately 2.54084. Now you might be wondering, why do we have these two different methods? Why do we bring up these two at all if we already have the midpoint rule? Is one better than the other? Well, there are formulas that tell us how big of an error in the approximation this can be. And don't think I'm going to prove these for you. They're really complicated to prove, and I don't want to get into that. But it is important to know that these errors exist, that these formulas for the errors exist. I'll start off with the one the book doesn't actually mention, the midpoint rule. Here, the error in the midpoint rule is no more than b minus a cubed over 24 n squared. So we're using n, where you have an integral of f from a to b. We break it up into n pieces. Then we have the maximum between a and b of the second derivative of x, or the absolute value of that. So, actually, before I explain anything, let's just write down the other ones. We have a similar formula for the trapezoidal rule. We have b minus a cubed over 12 n squared, max from a to b of the second derivative of f. And finally, Simpson's rule. Here the error is no more than b minus a to the fifth power over 180 into the fourth times the maximum from a to b of the fourth derivative. So a few things to note. These formulas depend on the higher derivatives of the function. Basically, the midpoint and trapezoidal rules give the same answer if the second derivative is 0, or give the exact answer. If we use the midpoint rule or the trapezoidal rule when the second derivative is 0, because we have, in that case, we just have a straight line, they give us the exact right answer. So in a sense, what we're doing this is that using the idea that the second derivative tells us how far off from being a straight line we are. And that how far off we are from being a straight line gives us errors in the actual computation of midpoint and trapezoidal rules. Simpson's rule is pretty similar, but we're using parabolas. Remember, a parabola is what we get if we had a third derivative equal to 0, but it turns out we can even go a little bit further and look at the fourth derivative. That's actually an advantage of Simpson's rule. The other point here is their relative strength. We want the error to be as small as possible, and all the stuff in Simpson's rule, for instance, like the higher derivative here, the fourth derivative, but also the fact that we, instead of having n squared, we have n to the fourth on the bottom. This means that Simpson's rule is going to be significantly more accurate than the others, at least in theory. Especially when we increase the number n, that means Simpson's rule's error is going to decrease at a much faster rate. So in general, if you really need a good approximation, you would pick one of these rules, you would increase the n until you get to the point where it's as accurate as you need it to be. And you might use these formulas in order to force that error to be within a certain bound. But also look at the midpoint and trapezoidal rules. These error formulas are pretty much identical. We have the same second derivative, we have the same cube of b minus a, we have the same n squared. The only difference is we have a 24 on the bottom of the midpoint rule, whereas we only have a 12 on the bottom of the trapezoidal rule. That means, because we're actually dividing by an extra 2 on the midpoint rule, we have the surprising fact that the midpoint rule turns out, in theory, more accurate than the trapezoidal rule. So you could say that the extra annoyance of having to find midpoints of the subintervals, rather than just using the endpoints like we did in the trapezoidal rule, turns out to actually be a benefit. So the trapezoidal rule might be easier to actually use, but the midpoint rule is a little bit more accurate. And Simpson's rule is actually way more accurate than either of the other two. But the idea behind Simpson's rule is definitely more complicated. Let's go ahead and do an example of using these error formulas. Let's look at problem 38. In problem 38, they give us an integral from 1 to 3 of 1 over x dx. Of course, this is something we can actually find exactly. Remember that the integral of 1 over x is a natural logarithm, and because the natural logarithm of 1 is 0, this turns out to be the natural logarithm of 3. But we're going to assume here that we don't have a way to find logarithms. We don't know what the numerical value of the natural logarithm of 3 actually is. So we're going to ask ourselves, let me just read the directions. Use the error formulas to find n such that the error in the approximation of the definite integral is less than 0.001. Or sorry, 0.0001. Using, well, they want the trapezoidal rule and Simpson's rule. I'm just going to do Simpson's rule. So So that's my question. And we'll go ahead and find that approximation when we find that in. So basically we want, so the absolute value of e here is what we're referring to our error as. Technically here you could say e is the difference between the true value, if we had the exact value of the integral, minus the approximation that we got from these rules. We're going to use this formula here, which actually, before I even go ahead and start writing out e, we need to find derivatives. We're going to remember our function here is f of x is 1 over x. The first derivative, actually, let's go ahead and even turn this into a power so it's easier to work with. The first derivative, when we differentiate x to the minus 1, is a negative x to the minus 2. If we differentiate that again, well, now we need to multiply by negative 2. That's actually going to cancel out the negative to get 2 times x to the negative 3. The third derivative, we differentiate it again. This 2 gets multiplied by a negative 3 to give it negative 6. And the new power is negative 4. And finally, the fourth derivative, just differentiating again, negative 6 gets multiplied by negative 4 to give it positive 24 x to the negative 5. Or you could now write this as 24 over x to the 5th if you want. On the interval from 1 to 3, the x to the 5th on the bottom is at its smallest when x equals 1. If we have a bigger x than 1, we're going to be dividing by a bigger number. So that means our fourth derivative is at its maximum at x equals 1, and that maximum is 24. That means we have an error from Simpson's rule that's no more than b minus a. Actually, I'm just going to write out the formula again. B minus a to the 5th over 180 into the 4th, maximum from a to b of the absolute value of f fourth derivative. And we know in this particular case, b is 3, a is 1. So we have 2 to the 5th over 180 into the 4th, and then times 24. We said this was 24. Or in other words, this is 64 over 15 into the 4th. Now, we want this error to be less than 0.0001. So we want this, if we can make this value here less than that, than 0.0001, then we know the error is going to be less than that too. We don't know what n is. That's what we're trying to find. So we're going to essentially solve this inequality for n. First thing, we just kind of, well, actually, I'm going to reciprocate everything first. That's going to change the direction of my inequality. But then I'm going to also take the 64 and the 15 to the other side. We end up getting n to the 4th is greater than, let's say, 42,666, and then actually 0.6 repeating. That looks like a really big number, but remember, we do have the n to the 4th power here. So we are going to take the 4th root of this. When we take the 4th root, we have that n is greater than, I'm just rounding it to 15. Of course, I guess we can even say greater than or equal to. But because we're going to be using Simpson's rule, we do need an even n, so we're going to have n equals 16. This is the n that we need to ensure, at least by this formula, that we do have an error less than 0.001. So, let's go ahead and do it. Remember, we have our interval from 1 to 3. Our delta x is going to be 3 minus 1 over 16, which is a 1/8. We have endpoints of 1, 9/8, 5/4, 11/8. Actually, I'm just gonna write all of them. 13/8, 7/4, 15/8, 2, 17/8, 9/4, 19/8, 5/2, 21/8, 11/4, 23/8, and 3. Those are endpoints. There should be 17 of those if I didn't mess something up. That means our integral, or really the natural logarithm of 3, is approximately equal to 1/3 that comes from the formula for Simpson's rule, times our delta x of 1/8. We plug these into our function. Our function is just 1 over x, so actually that's a really easy thing to do. We just take the reciprocals of those. Reciprocate 1, we get 1. Reciprocate 9/8, we get 8/9. But remember, we do need to multiply that by 4. Then we have 2 times the reciprocal, so 4/5. 4 times the reciprocal of 8/11. 2 times 2/3. 4 times 8/13. 2 times 7/4. Sorry, 4/7. 4 times 8/15. 2 times 1/2. That one's nice. 4 times 8/17. Notice these are all multiplied, by the way. It's not 4 and 8/17. 2 times 4/9. 4 times 8/19. 2 times 2/5. 4 times 8/21. 2 times 4/11. 4 times 8/23. And then finally, we just have a 1 times 1/3. So remember here we have 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So make sure we have that pattern correct. And then I got to tediously put this into a calculator. It did take me a while, but I got an approximate answer of 1.098620004. Well, in this particular case, we do have the exact value. Natural logarithm of 3, when just plugging that into a calculator, is 1.098612, and so on. So notice here that we did actually get even closer than the 0.0001 that we wanted. If we just had that, then we could have this 6 not be a 6. It could be somewhere between 5 and 7. Of course, the error equations that we had here don't really tell you the exact value of the error. They just give you an upper limit on how bad it could possibly get, the worst case scenario. In practice, we're going to get closer than what these formulas predict. But those are the best bounds that we have. There are some really nasty functions, maybe not so nasty, but some functions that actually that take those to their limits, and we can't get any closer than that. But don't really worry too much about the error formulas for the exam. Or don't worry about them at all, actually. I'm not going to be asking you to use those error formulas. They're mostly there to say that, yes, we do have rules for how bad of an error we can get, how good of an approximation these numerical integration techniques actually are. I will be asking a couple of numerical integration problems, but it'll just be a matter of applying the midpoint, trapezoidal, or Simpson's rule to one integral with a relatively small n. I'm not going to make you do 16 like we did here. Probably I'll pick maybe 4 or 6. Two's too small, and if I'm going to use Simpson's rule, I need it to be an even number. Probably more leaning towards 4, just because if you can show me a pattern, that you know the pattern for the trapezoidal rule and Simpson's rule for 4, it kind of implies that you know what you're doing at least. So make sure you remember those patterns, and remember that what we divide delta x by out in front. With the trapezoidal rule, we had a 2 we divided, and with Simpson's rule, we divided by 3. If you remember those patterns and those factors out in front, you should be fine. But that's all we have for the rest of the course, actually. That is the end of our course. There is more to the book, of course. We actually only got halfway through the book. There's plenty of other topics, but we don't have time for those. I'm not entirely sure why we don't have a Business Calc 2 or something like that, but that is all we're going to cover in business calculus. So I'll leave it off here, and I'll see you guys at the final. Take care.